Well, of course, I'd like to thank the organizers very much for the invitation to speak at this wonderful event. It's such a great pleasure to help celebrate Mike's 60 years of rock climbing and hanging out in bars and doing mathematics as well. I guess every real sort of mathematical breakthrough is something of, going against the conventional wisdom about it. I mean, almost by definition, that's certainly true with Mike's proof of the four-dimensional Poincare conjecture. In fact, he actually cost me $50. This is something I've done. So in 1980, around about 1980, just to give an example of what the prevailing kind of view of low-dimensional topology was, I somewhat recklessly, I guess, made two bets, two $50 bets, one with Rob Kirby, and I think one with John Hare. Both with Rob, he tells me, okay, you got $100? The Sierra Club got $100, okay. And so the two bets were that by the end of the decade, that was the 80s, the three-dimensional Poincare conjecture would be settled, and the four-dimensional one would not. And that seemed a really, it's like taking candy from babies, right? It's an obvious, I was clearly going to win both these, So within a year, Mike had cost me the first $50. I sort of held on to a categorical technicality for a brief period when he had a smooth hypothesis and a topological conclusion, but that didn't last long, and so I had to pay up. And meanwhile, of course, Thurston was talking very optimistically about, his hyperbolic Dehn surgery and so on, which is related to what I'm going to talk about today, I suppose. And it looked very much like he was quite optimistic that the three-dimensional Poincare conjecture would be proved set. So that's okay, Mike. I don't mind it. It was a small price to pay for that to do. Okay, well, the organizers have asked me to give a kind of survey talk or general talk about acceptable Dehn filling. So I apologize. Many of you may have heard me talk about this sort of stuff before, and I certainly have. But I'll try to give some sort of overview of a program to understand acceptable Dehn filling and what's been done and what remains to be done. And so maybe there's something. If some of you young students out there have trouble sort of visualizing n categories for n greater than 2, there's some problems where you can work on here instead. So, right. So, exceptional. I guess I'll get lots of exercise here. So what's the setting? Well, the setting is, the setting is a Dehn filling. So if we start with a compact, connected, oriented, three-manifold, and I'll always look at the case where, we put lights out, is it okay? I'll always look at the case where M has boundary, a collection of tori, possibly one, possibly more than one. And so what's Dehn filling? I mean, you, as you all know, you attach a solid torus along some torus boundary component, and so we're going to pick. There'll be some implicit boundary component T0, which usually won't be mentioned, and we're going to look at essential simple closed curve alpha on that particular torus boundary, and then the Dehn fillings on that boundary component are parameterized by the isotopic classes of these alphas. So you attach a solid torus so that alpha binds a disk, and that's M alpha. That's alpha Dehn filling. And this is an old construction, and in the context of hyperbolic three manifolds, it was studied by Thurston. And in particular, he showed that if you start with a hyperbolic manifold M, in other words, if M minus the boundary has a complete hyperbolic structure, so these boundary components correspond to these sort of cusps. Then if you start doing Dehn filling on this thing, then for all but finitely many choices of alpha, you're going to get a hyperbolic manifold again. And of course, this gave a way of kind of a very general way of approaching the geometrization conjecture, because every closed three manifold can be obtained by Dehn filling on the complement of some link in S3, and so if you really understand, and you can assume that link's hyperbolic, and so if you could somehow understand what happens to the hyperbolic structure under these Dehn fillings, then And of course, this is exactly what Thurston did, but again, it cost me another $50. He didn't quite finish it off. But so if you take a generic sort of hyperbolic three-manifold M with torus boundaries, then probably there'll be no Dehn fillings will give you a non-hyperbolic manifold. Every Dehn filling will give you a hyperbolic manifold generically. But of course, there are certainly exceptions, and you want to understand the exceptions. So the first remark is it's probably unrealistic to try to understand all the exceptions in the sense that I just mentioned, because, for example, if you take any hyperbolic knot in S3, and of course there are infinitely many such, most knots are hyperbolic, then the exterior of that knot, if you take that to be the manifold M, then there's going to be a Dehn filling that gives you S3, which is not hyperbolic. And so, you can't, looking at a single Dehn filling, if you wanted to understand that, you'd have to understand all hyperbolic knots in S3, for example, and that's a little bit too ambitious. On the other hand, it's extremely rare. It seems to be extremely rare to have, for a manifold M, to have two distinct non-hyperbolic Dehn fillings, alpha, beta, along this given boundary component T0. And so, it's not perhaps totally unrealistic, and I'll try to explain in what sense it might be possible to do it, to try to understand all such triples, I guess. All such triples, hyperbolic M, two distinct slopes on some torus boundary component that give you a non-hyperbolic manifold, that would be an exceptional Dehn filling. Okay, well, so the sort of the classical example here, of course, is the figure 8 knot, the first hyperbolic knot. Maybe the first thing to say is that, so this was worked out by Thurston, the figure 8 knot exterior, M1. So if we call EM the set of exceptional slopes, there are exactly 10 of them for this manifold. 1 over 0. I'm parameterizing these slopes. For knots in S3, I'll parameterize these slopes in the usual way, but if you don't know what that is, don't worry about it. Okay, so 1 over 0 is the meridian, so that's the filling that gives us back S3. And then we have 9 others, 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Now actually, it turns out that a slightly more sensible measure of these exceptional fillings, rather than just how many there are, is how far apart they are in the sense of intersection number. And so if you have so one feature, which there are many reasons for it, if you have two exceptional Dehn fillings, alpha, beta, on a given M, the intersection number of those two curves has to be quite small. And so we call that intersection number delta, and informally refer to the distance between alpha and beta. And so you can look at delta of a hyperbolic manifold M now being the maximum. Again, with this torus component T0 sort of implicit in all that. Delta M is just the maximum distance between any two exceptional slopes. So for the figure 8 knot, the total number of exceptional slopes is 10. The maximal distance is 8, realized by plus or minus 4. So that, in general, I have to say that it's a little hard to see, that these fillings along these slopes give you non-hyperbolic manifolds. 1 over 0 is easy, you just get S3. 0 is also easy in this case because, as you know, the figure 8 knot component is fibered. It's fibered over the circle with fiber punctured torus. So the longitude, the 0 slope, bounds this punctured torus. So when you do filling along that 0 slope, you now get a torus bundle over the circle. And of course, that's non-hyperbolic. Let me just at least show you why the plus or minus 4 fillings are non-hyperbolic. So maybe I'll do this over here. So here's this is one of the few cases where we can actually see why these fillings are non-hyperbolic. So here's the figure 8 knot, and that surface indicated there, that's a non-orientable surface with whose boundary is the knot. It's a once punctured Klein bottle, and the boundary, if you think of that as a surface in the exterior of the knot, the boundary of that once punctured Klein bottle represents a certain slope on M1. For reasons will become clear in a minute, I'm calling the figure 8 knot exterior M1. And you can figure out what that boundary slope is. It's 4. In other words, it goes once round longitudinally, but it links the knot 4 times. And if you haven't seen that before, it's a nice exercise to work out why it's 4. And here's a hint. The 4 is not the same 4 as the number of crossings. Okay, so it's a different 4, but it's still 4. And so, again, when you do 4 filling, when you attach a sort of torus so that boundary slope, that slope 4 bounds a disk, you see, that's going to cap off this punctured Klein bottle. And you get a manifold that contains a Klein bottle. Well, you can't be hyperbolic. In fact, it turns out that in this case, if you take a regular neighborhood of that Klein bottle, the boundary that will be a torus, you'll twist it out and the Klein bottle. That torus actually turns out to be incompressible in the manifold. And because this knot is amphichiral, it's according to its mirror image, then if you do 4 surgery, that's the same as doing -4 surgery up to orientation. And so that's why these things are called pairs, plus or minus 1, plus or minus 1. Anyway, so you see that 4 surgery and -4 surgery on the figure 8 knot both give manifolds that contain incompressible tori. So they're not hyperbolic. And the intersection between 4 and -4 is 8. Well, so this is the simplest example, the simplest sort of hyperbolic knot, the simplest example. And in fact, the one nice thing about this subject I keep on saying is that the simplest examples are always the worst. And so, in fact, it never gets any worse than this. In fact, yes, so there are no known, of course, in the context of knots, one talks about Dehn surgery rather than Dehn filling, but the same thing. If I might borrow a joke from my bandmate Justin, who's, I don't know if he's probably not here, but this knot is the Michael Jackson of hyperbolic manifolds, and it has the maximum number of exceptional surgeries. And yeah, I thought that was a good joke. And so, in fact, in substance, this is now known to be true. So here I'm revealing this here. A fairly recent theorem of Lackenby and Meyerhoff, actually, that yeah, for any hyperbolic manifold M, you never have exceptional fillings at distance more than 8, and you never have more than 10 exceptional fillings. So that's very nice. That's sort of a really good start. A fairly recent theorem, but I mean, that's a very good start on understanding these exceptional pairs of fillings. Okay. Well, let's move on and look at another. I'm now going to get confused here. The logistics of this. Okay. So here's another set of examples which is sort of well documented. So here's a second example. We start with a hyperbolic link. The Whitehead link, well-known link, well-known hyperbolic link, and let's call the exterior W. And so I want to focus on 4 manifolds, M1, M2, M3, and M4, obtained by Dehn filling on one component of the Whitehead. And it doesn't matter which component you take because they're interchangeable. And so if you do one filling, you get the figure 8 knot exterior. And well, there are a couple of other, at least 3 other fillings, -5, -2, you get sort of well-known manifolds. M2 is the so-called figure 8 sister manifold. It's a sort of mutant of the figure 8 exterior. Anyway, these 4 manifolds were in particular studied by Hodgson and Weeks quite a long time ago, and they're hyperbolic manifolds. Okay, so I would emphasize these slopes that I'm talking about, these are not exceptional fillings. These actually give hyperbolic manifolds with a single cusp, a single torus boundary. But they're interesting in as much as those manifolds have pairs of exceptional fillings at relatively high distance. Namely, they have toroidal fillings, they have fillings that contain incompressible tori at distance 8, 8, 7, and 6 respectively. And we've just seen this for the figure 8 knot exterior, and it's true for the others as well. Okay, so here are some manifolds that have delta 8, 8, 7, and 6. And so it seems that these are the only ones. No one found any others with pairs with a pair of exceptional filling slopes at distance 6 or more. And so one conjectures that these are the only ones with delta 8, 8, 6. And this is not proved, but I'll say a little bit more later about some more things that are known about this. Some things that are known about this. First of all, that any manifold with a pair of closures at distance sigma, the boundary just has to consist of a single torus. More generally, it has to be a rational homology circle. And a much deeper result, proved recently by Ian, in fact, there are only finitely many hyperbolic ends that have a pair of closures with distance 6 or so. So this is great. It's a finiteness theory. See, we want to classify, right? The whole point was that can we understand all such M alpha betas? Well, maybe we can. I mean, there are probably only 4. At least we know there are only finitely many. So maybe there's just going to be some finite list of these things, and then we can all go home. Well, of course, that's not quite true, right? But so let's see. So let me point out that this finiteness that Ian showed for distance greater than 6, it sort of immediately fails when you get to distance less than 5, but for fairly trivial reasons. I mean, so here's another example. The third example, this is a well-known hyperbolic link, the Whitehead sister link. Again, it's related to the Whitehead link in a certain way. I mean, they're both fiber, both a circle with fiber punctured tori, and you just sort of, if you change the monodromy by multiplication by -1, the elliptic involution, okay, then you get this other guy. So this is a hyperbolic two-component link. It's actually the -238 pretzel link, if you like. And so it has two boundary components. Its exterior has two boundary components, T0 and T1. And now it's a fact, again, it's not immediately clear, but one can show this in many ways. There are actually a pair of slopes on T0, say, with intersection number 5, such that those fill in the toroidal manifold. So there are a pair of exceptional slopes on T0 at distance 5. In fact, they're homeomorphic manifolds. And now you see, because you've got this other boundary component to play with, you can use this example to generate infinitely many one-cusp examples. Because you just focus on the other boundary component, T1, and for infinitely many choices of gamma on there, when you do filling on that component, you're going to get a hyperbolic manifold by Thurston's finiteness theory, you see. And again, because when you filled in on alpha or beta originally, you got something that was non-hyperbolic, it's easy to see that for infinitely many choices of gamma, that's also going to be true once you fill it on T1 as well. And so this one example with two boundary components will generate infinitely many examples with one boundary component. But of course, they're all derived from that same one. And so there's an obvious sort of definition here of sort of ancestral finiteness. I mean, so we can modify the question, you know, the set of these things is not going to be finite, but maybe the set of exceptional M alpha betas, maybe it's ancestrally finite in the sense that they all come from some finite set of things with possibly more boundary components in the sense I just outlined. So I'll say more about that. So anyway, here's a more precise definition, and I mean, you can make it up, but here's a more precise definition of ancestral finiteness. In other words, we're asking, is there some finite set of hyperbolic guys N alpha beta here with pairs of exceptional slopes, such that every exceptional M alpha beta is obtained from some guy in that finite set just by filling along some subset of the components that, other than the one that you're focusing on, T0. And it's not so hard to show. There's a little bit of fussing, because if you think about it, I mean, I'm really insisting, you see, that the slopes alpha beta are exceptional slopes for N as well as for N. But a little bit of fussing, essentially theorem due to Jorgensen and Thurston tells you that a set of exceptional guys M alpha beta will be ancestrally finite. They'll come from a finite set of things in this sense, if and only if the set of volumes of the manifolds in question is bounded above. Yes?
You mentioned system twice. Is there a general definition of a system?
Well, I mean, yeah, tell me. A general definition of system.
It's just related, like
What?
I said, by hyperbolic
Yeah.
evolution, or elliptic evolution lines on surface.
Right. I see, right, I mean, so the figure 8 is fiber with your fiber punctured torus, right? And if you change the monodromy, if you multiply the monodromy by minus the identity, then you get this other guy. And it's going to share, it's going to have the same volume, you know, it's going to share all the properties of of the original manifold.
So it's different,
Hmm?
how does it differ from the notion of mutation?
Well, I think it is a special case of mutation. I mean, people use mutation differently, right? You can do mutations, but yeah, for punctured spheres and punctured tori and GH2 guides. I mean, there's a kind of thing. Okay, so let's leave ancestral finiteness for a minute, and let's sort of just focus on. I'll come back to this, but so let me sort of outline a sort of program for understanding these exceptional fillings. Which so the first thing to note is that after geometrization, you see we now know exactly what it means to be non-hyperbolic. So if you've got a slope alpha, such that when you fill on this guy m, you get m alpha, and suppose it's not hyperbolic, so alpha is an exceptional slope, then the manifold you get, it's either reducible, contains an essential sphere, so I've indicated that by S. You see, and then, or it's toroidal, contains an essential torus, and you do that by T, or it's S3, or it's a lens space, and I've indicated that by SH and PH, H standing for Hagar. So I want to kind of emphasize that, you know, some of these surfaces of sort of high Euler characteristics play a key role in these exceptional, well, I mean, the theory of exceptional free manifolds, obviously, we all know that, you know, they coming on spheres, coming on tori, so you're either reducible toroidal, the 3-sphere, in which case you contain a Hagar sphere, or you're a lens space, in which case you contain a Hagar torus, or, and this is, as we'll see as the talk progresses, the problematical case is that you're a small cipher. So you're a cipher fiber space, but you're atoroidal, and you're not a lens space or SC. So for example, in the closed case, the small cipher guys are ones whose sort of orthofold is the 2-sphere with three cone points, 3 exceptional fibers, multiples A, B, and C. So as we'll see, that's the sort of class but by which we know the least with respect to this exceptional filling sum. But anyway, the idea is, I mean, if you want to, obviously there are finer classifications. You can look at different lens spaces. You could look, you know, whatever. I mean, but still, I mean, this is a fairly a first sort of pass, crude sort of classification of non-hyperbolic manifolds. Reducible toroidal S3 lens space or small cipher. And so here's a sort of outline of a program. For any pair of these classes, let's first try to find out what's the maximum distance between any 2 slopes that have the property that, you know, one of the fillings belongs to the class A, maybe it's toroidal, and the other filling is in class B, maybe it's a lens space, okay? And so for each pair, let's try to understand what this maximum distance is. And then once we've bounded that, then let's try to then get in there and completely understand the manifolds and the slopes that realize that bound. So find the ones that you know, delta actually equal to delta alpha. I'll say more about this in a minute. And then finally, of course, you want to understand everything. So you want to understand the things that, you know, where the fillings in question belong to these classes, but the distance is less than this maximal distance. Now, of course, the third part is the one that obviously is kind of hard. I mean, I should say that, you know, this intersection number, I mean, you know, as I say, the intersection number can't be more than 8. And when it is 8, you see, or 7 or 6 are probably only 4 examples. And you get to 5 or more examples. As this delta decreases, you get more and more possible exceptional fillings. And so for very low values of delta, like 1, we'll see in a minute, in fact, like for 1 and 2, it's probably a little bit unrealistic to expect to classify everything. But anyway. So let me, so there's been quite a lot of progress on this program. In particular, if we get back to that original conjecture that I made, that the distance 6 or 1 is only 4 examples. In fact, this is actually true modulo this small cipher case. So this is an example of, if you put together all the things that are known now, if you have an exceptional pair, M alpha beta, with distance greater than 6, provided neither of these 2 non-hyperbolic fillings, M alpha and beta, provided neither of them are these Alford small cipher guys, then in fact we know that M does have to be one of those for manifolds that we know and love. So, as you'll see, I mean, this is, yeah, it's this class Z that, the small sample class that's the problematical one, actually. So again, let me summarize what's known about this program. So there's the program. So the first part of the program was to determine the maximal distances between various types of exceptional fillings, you see. And so here's a table, which I'd like to show. It's updated. Actually, this hasn't been updated. I mean, there's been no change in this table for quite a while, actually. So here's what I've indicated, that I haven't listed Z because the maximal distance between a pair of exceptional fillings where one of the guys, let's say M alpha, is a small cyclone. I mean, that's unknown in all cases. So there's no point in listing that. I mean, there are some results, but the best answers aren't known. Easy to conjecture what they are, but for the other four classes, so this table is meant to indicate, you know, well, first of all, let me say that in the case where the manifold that you start with has more than one boundary component, then everything is known. So things get easier when you have more boundary components. So really the interesting case is when you start the manifold with one boundary component, so you use a filling unit, a closed manifold. And so this is supposed to indicate, you see, you could get S3, that's S, you could get a lens space, that's D, you could get a reducible manifold, that's S, or you could get a toroidal manifold. And so what's the maximal distance between these various pairs? And well, that's indicated in that table. So as you see, most of the numbers are known. There's only two that are not known. So for example, the 0 in SH, that says that, you know, if you have hyperbolic manifold and one filling, M alpha, gives you S3, well, that means you have a hyperbolic knot in S3, and then no other filling can give you S3. So that entry is the complement theorem. And similarly, SHTH, that says if you're not in S3, and then you something give you a lens space, well, that can happen, as we'll see. But if it does, the distance between the two slopes, in other words, the distance between the meridian and S3 and this other slope that gives you a lens space, has to be 1. And similarly, two lens space fillings, TH, that's also 1. So those two entries are a consequence of the cyclic surgery theorem, and so on. And right, and so the other entries, the two question marks, let's explain those. So SH and S, so one of the fillings gives you the 3 sphere, and the other filling is supposed to give you something reducible. Well, it's known that if this does happen, then the distance has to be 1. But in fact, it shouldn't happen at all. And this is the cabling conjecture, which I'll mention. And so that entry, that first question mark, should really be minus infinity. But that's a famous open problem. And so I'll mention some recent progress on this a little later on, but that's still wide open. So given any hyperbolic knot, then no Dehn surgery on it can give you a reducible manifold. The other case that's not known is THD. So in other words, you know, two fillings, one of which gives you a lens space, one of which gives you a toroidal manifold. It's almost known. It's known. There are infinitely many examples that realize this is 3, and it's known that it can't be more than 4, and so it should be 3. But so again, right at the end, I'll mention some sort of. So this is the first part of the program, just determining these maximal distances. And so, you know, okay, well, there's some work to do, but that's fine. We've got to find things to do, you know, now that the geometrization trajectory is improved. What about the second part of the program? That's, you know, actually classifying the manifolds and the slopes and actually realize these things. Well, again, actually, obviously less progress there, but in some cases, no. Well, okay, the SH case, I mean, that's vacuous, right? SH and T. So let's go back to the first table. That entry is a 2. So what that says is that if you have a knot in S3 and you have a hyperbolic knot in S3 and you have a Dehn surgery that gives you a toroidal manifold, then the intersection number of that slope with the meridian is at most 2. And in fact, there are examples where it is 2. And this check here says that the examples that realize that value of 2 are completely determined, completely classified. And I'll say more about this in a minute. And similarly, ST, that's, you know, when you have a hyperbolic manifold and a pair of fillings, one of which is reducible and one of which is toroidal. Again, it's known that the intersection number can be more than 3. And again, the examples that do exist in this are completely determined. I mean, there they are, they're completely explicitly determined. So, and same with the tori. With the tori distance 8, there are only 2 examples of the figure 8 and the figure 8 system. And it's known that those things are. So, again, there's some progress there. Now there are 5 question marks. Of course, 2 of the question marks, we don't even know what the maximum distance is. So we got, you know, okay. The other 3 question marks, well, we understand. So there's still some work to do there. And then finally, of course, you want to really understand everything. So you want to now look at examples where the distance in question is less than the maximum distance. And there, of course, many more examples start to show up, and it gets harder and harder. So this has been done at least for the case of 2 toroidal fillings, all the way down to distance 4. So that's something. But in general, of course, that's not going to be so easy to do. So let me focus on the first row. The first row of this. By the way, those of you from Texas A&M, the lower half can actually be calculated. The lower half of the table as well. Yeah, okay. I can explain that to you after. Okay. That's a Texas joke, I guess. You know, this reminds me, in my misspent use, okay, there's an advice to you guys who are looking for jobs and that. I once gave a job talk, right, at someplace, I don't know where it was, and I was talking about knot concordance. And I started the talk, you know, I had this little spiel about, you know, knots, it's very interesting, you know, and you could form connected sums, and you get a commutative associative operation, and there's a 0, you know, the odd knot, and so you get this semigroup. But there are no inverses, and everybody knows semigroups are, you know, totally uninteresting, boring things, you know. You really want to make this a group, and so if you have a weaker equivalence relation with concordance, now you get inverses, and you get a group, and everything's wonderful. Yeah, I thought it was quite a good talk, you know. And at the end, someone said, you know, our chairman works in semigroups. So find out what the chairman does before you do this. That's a true story. They did offer me a job, actually. But anyway, I'm just going to, so obviously an interesting, you know, historically, well, so the special case of all this is when we just look at knots in S3, and so that sort of corresponds to the first row, if you like, of those tables. You see, if you do have a hyperbolic manifold M, then there's some filling M alpha gives you S3. Well, another way to say that is that M is the exterior of a knot, K in S3, and alpha was just the meridian of the knot. And so in that case, we can write sort of M beta, we'll write K beta. We think of you know, M is the exterior of this knot, K. So a good example here is the -237 pretzel knot. Remember the -238 pretzel link came in earlier? That was like this. So this guy's interesting. So here's what's interesting. Again, the exceptional slopes of this guy we worked at. I'm afraid I can't remember who worked that out first. But anyway, it turns out that these are the exceptional filling slopes on this knot. There's infinity. One of which that's the one that gives you the free sphere. So that's always there. That's S8. And then there's 16, 17, 18, 18 and a half, 19, and 20. And so let's see, 18 and 19, they give you length spaces. So that's that TH. So you get 2 length spaces. 17 gives you one of these small cycle fiber spaces. In fact, I just find a fundamental group even. And then 16, 37 over 2, and 20, they give you toroidal manifolds. And so this is an example that shows, you see, that apart from possibly getting a reducible manifold, which, as I've said, is conjecture never happened, I'll say this in a minute. This illustrates all other possibilities. I mean, here there's one filling gives you S3, two fillings give you a lens space, three fillings give you a toroidal manifold, and one filling gives you a small size product case. So all these other cases can actually happen, and here they're actually happening with the same knot. Now, of course, one thing you notice about these entries is that they're all integers except one. And so this 37 over 2, this denominator 2 is the intersection number of that slope with the meridian. And this is an example of the first table you see, SHT. So there's a toroidal filling and an S3 filling at distance 2. And in fact, I'll say more about this in a minute. There are infinitely many examples of this kind, and they're completely classified. That's table 2. That's the check. So again, let's. So let me focus on the case for a minute. Let's focus just on the case of not complements in S3 and see what's going on there. So first of all, like I said, the case of getting a reducible manifold, that should never happen. And so that's the cabling conjecture, which was raised quite a while ago by Gonzalez, Acuna, and Short, that if you have hyperbolic knot in S3, then you never get a reducible manifold by surgery on that. You might wonder why it's called the cabling conjecture, but I won't go into that anyway. What about toroidal? Well, as I said, the -237 guy, that has this half-integral toroidal surgery. Well, it turns out there's actually infinitely many such things. There's an explicit infinite family that was constructed by Yugami Munoz. It's an explicit parameterized sort of family. Each one's a hyperbolic knot, and each one has a toroidal surgery with denominator 2, so distance 2 from the meridian. And like I said, John Ruby and I showed a while ago that, in fact, these are the only examples. In fact, more generally, distance 2 is the maximum, and if you are in distance 2, then you have to be one of these knots. So, in other words, your hyperbolic knot in S3, if you have a toroidal Dehn surgery where the denominator is greater than 1, so it's not an integral surgery, then in fact it has to be exactly 2, and the knot has to be one of this explicit family. So that's a kind of answer what we're trying to get for all these exceptional fillings. That's what I'm suggesting, that maybe we should try to get to classify all such data. Now, but it certainly gets hard. Other toroidal fillings, you see, the thing is that when the distance is 1, in other words, well, I mean, there's just perhaps too many examples to really hope to simply classify them. But so there are many examples of hyperbolic knots with toroidal fillings that are integral. Well, I mean, my 237 pretzel knot has a couple of 60, 50, and so as I say, as the distance, as the distance gets smaller, it gets harder and harder to really classify these things. But that's, so I've talked about reducible, toroidal, this is for knots in S3, and the other class then, well, there's the small cipher class, but the lens spaces. So let me say something about lens space. So here we have the famous Berge knot, of which -237 is just a particular example. So this is a wonderful sort of construction, goes back to unpublished work of John Berge in 1990. So the idea is you start with a genus 2 Haggard surface in S3. There it is, F. And so it cuts SU2 handle 2 genus 2 handle is WW prime. And he looks at knots K that sit on that surface F, and he looks at the knots that have this property. Suppose you have a knot K that sits on there with the property that if you add a 2 handle along that knot to W, you get a solid torus, and similarly, if you add a 2 handle to W prime along the knot, you also get a solid torus. In other words, well, there's an easy sort of algebraic characterization of when that happens. It says that the element of the fundamental group of W prime represented by K is a basis element. So what do you call these double primitive knots? Well, if you have such a knot, and it turns out that there are infinitely many of them, in fact, Berge has completely classified such knots, then you have a knot with a lens space surgery, because it's easy to can see that just by the way it's been set up. If you take beta to be the framing slope that's determined by the fact that this K is lying on this surface F, then it's clear that if you do beta surgery, this is like what Marty said in his talk. You're gluing in this solid torus, and you think that solid torus is the union of some two handles, and one of them is attached to W and the other is attached to W prime. Anyway, it's easy to see that what you get, if you use that framing, is just WK union W prime K glued along the money. Well, that's two solid tori glued along the money, that's a lens space. And so there are infinitely many Bernoulli knots, and as I say, it's a very interesting set of knots. And here, the conjecture is, the Bernoulli conjecture, made by Bernoulli back in 1990, still open, that these should be, that if you have a hyperbolic knot in S3 and a surgical lens space, then K should be a Bernoulli knot. And the slope beta should come from, this representation of K has a Bernoulli knot on the surface. So this is still wide open, but there's been a lot of renewed interest in this, using Hagar-Fur homology to study this. And of course, it's given rise to the concept of L space, which is it's something to which all arguments in Hagar-Fur homology that apply to lens spaces also apply too. I'm sure that was ungrammatical, but you know what I mean. So this is still wide open. There's still a lot of work going on, I think, on that conjecture. That'd be a great, it's a nice open problem. There's the Cabling conjecture, which is still open. There's a very interesting recent result by Josh Green on this, that at least what he calls the realization part of the Bernoulli conjecture. So in other words, at least the lens spaces you get have to be one of the ones that you get from a Bernoulli knot. So that's a lot of very supportive. I should say that, okay, well, maybe I'll leave that up. Yeah, so I guess one class I haven't mentioned, and I'll mention this at the end, but I mean, I haven't said anything about small cipher, Z, this class Z. Remember minus 237 had this 17 filling, gave you a small cipher fiber space. In fact, there are infinitely many hyperbolic knots that have small cipher filling. And, but I think there's a sort of conjectured picture, which I never time to go into, as to what they should look like. But let me just at least say that the most naive picture there does not hold. See, there's a very natural generalization of the Bernoulli knots. Namely, you look at the genus 2 Hagar surface there, and you look at knots K such that with respect to W, they are primitive. In other words, when you add a 2 handle to W along K, you get a solid torus just like there. But on the other side, if you insist that when you add a 2 handle to W prime along K, you don't necessarily get a solid torus, but you get a cycle fiber space. Right? And there are many such things. I mean, typically, it will be a cycle fiber space over the disk with 2 singular fibers, and so on. I mean, okay, and so then, by the same argument, when you do surgery on that knot along this framing slope, you're going to get a solid torus union a cycle fiber space. And so that's going to be a cycle fiber space. And so these are so-called primitive cipher knots, as opposed to primitive. They're primitive on one side, but cipher on the other side. And the most naive conjecture is, well, the analog of the Bernoulli conjecture, that any hyperbolic knot with a small cipher thing filling would have to come from this primitive cipher. But unfortunately, that's just not true. So the picture is slightly, many of them do, but the picture is just slightly more complicated there, and I don't think there is more to be said, but there's not perhaps a really definitive sort of conjecture picture there as to what's going on. So that's why let me just finally say a little bit more about this ancestral finiteness kind of idea, and how one might try to even though there are infinitely many examples all over the place, maybe one can try to sort of codify them in some organized way. So here's a class of links that so much of this was introduced by Thurston in his notes. In fact, so I was actually lucky enough to be at the Institute in 1976, 77, and some of you others were there too, and that's when Thurston gave this famous lecture course on hyperbolic Freedman, hyperbolic structure and so on. And it was very, very, very interesting. This course was extremely sort of puzzling to sort of people like myself, obviously, who were trained as topologists, and suddenly there was all this hyperbolic geometry, which we thought went out with a lot of Chesky or something. And here it was back again. And I think some of them described Thurston's lectures as postcards from Mars, which is a very good description. But no, I mean, essentially, I mean, Frank was alluding to this. He's talking about Poincaré, right? And in the early days when people studied manifolds, they were very aware of the existence of hyperbolic structures on surfaces, and, geometric structures on surfaces. So one of the first things people did when they studied three manifolds was look for geometric structures. I mean, it wasn't that they missed it. I mean, it was clearly the first thing they looked at. It was the most natural thing to do. And the trouble was that, well, spherical structures, elliptic structures, they completely classify that way. Euclidean structures, they classify too. Hyperbolic structures, they couldn't find many examples. There were one or two very sporadic examples. The famous Seifert-Weber building Higglesworth, for example, and some others. But they quickly realized that, things like connected sums and tori precluded every three manifold from having a geometric structure based on a sort of constant curvature metric. And so somehow geometry kind of disappeared from two-dimensional topology and it was replaced by topology. And of course the great era of the 60s and 70s with Haken and Waldhausen and so on. And then in the 70s, of course, Thurston came back and said, no, you were missing the point. The hyperbolic structures really are there all the time. You just didn't see them, So it was really a return to the original kind of geometric point of view. And so one of the many things in Thurston, so he describes this class, a very general class of hyperbolic links, and that's he calls chain links. So I've drawn, these guys seem to play an important role. The guy on the top right is, it's a 5-chain link. Now there are clearly, you can make up the definition, there are clearly many 5-chain links, because you could twist them in different ways. This is actually a particular one called the minimally twisted one, and it's kind of special because it has a very large symmetry group. So that's, and it was noticed a long time ago, I think, that a lot of the small volume manifolds, like in the census, manifolds built up from small numbers of ideal tetrahedra and so on, tended to be obtainable as Dehn filling on the complement of that 5-chain. So there's a series. Here's the 5-chain. If I do one surgery on the appropriate component, I'll let you figure out which one it is, then you get the 4-chain, this particular 4-chain link. And if you do one surgery on the appropriately chosen component of that guy, you're going to get the 3-chain. You do one surgery on the component of that guy, you get the Whitehead link. So you can think of that as the 2-chain link. You do one surgery on one of that, you get the figure 8 link. So it's like the 1-chain. So you get this nice sequence of links. And this series seeks to account, in some sense, for most of the sort of exceptional sort of pairs of Dehn fillings. So in particular, Martelli and Petronio, in a paper, they completely describe all kind of exceptional fillings on the 3-chain link. And just recently, Rukama, in his thesis, he's completely described all hyperbolic fillings on the 5-chain link. So there's a very nice kind of picture that's sort of emerging. Maybe ultimately this is going to be some huge kind of periodic table of diagrams and various arrows that somehow account for all pairs except the fillings. So let me say a little bit more about conceptual finiteness, you see, in this context. So for example, let's look at that 4-chain link. Let's look at that 4-chain link. Well, it so happens that that guy, there's a couple of fillings on some boundary component at distance 2 that gives you toroidal manifold. So that's an exceptional pair for C4. Now remember I mentioned these Udavi-Munoz knots. They were the hyperbolic knots in S3 that had a toroidal filling at distance 2 from the meridian. Well, it turns out that whole infinite family really are descendants of that one example. In other words, that every Udavi-Munoz knot can be obtained from the 4-chain link just by suitably filling 3 of the boundary components. And then the other 2, you just do those fillings alpha beta, which were exceptional way back at the C4 level, and now they're exceptional on the one cup guy, and one of them is the meridian, gives you S3, the other one gives you the toroidal. So that whole family can somehow be explained just in that one. And so, as I say, the set of Udavi-Munoz knots, although it's infinite, it's actually ancestrally finite. It just comes from this one example. And so it's the kind of thing that you want in general. Now, unfortunately, of course, it's not quite true. In fact, if we go to the Berge knots, if you look at just the hyperbolic ones, there are sort of 8 families in Berge classified using. And for all but 2 of the families, these guys, with their 2 surgeries, namely the S3 surgery and the lens space surgery, they're actually descendants of a single exceptional pair on the 5-chain. See, if you do 0 filling, if you do infinity filling on the 5-chain, obviously you're just throwing away one of the components, and clearly that gives you a connected sum. So that gives you a number with a torus. And similarly, if you do 0 filling, it's easy to see, you can see an angulus there too. So 0 and infinity fillings on any component of the 5-chain will give you a non-hyperbolic manifold. And all the Berge knots, they're just obtained from that just by suitably filling the other 4 manifolds. But unfortunately, so that's a nice explanation, you see, of this ancestral finiteness of Freedman. But unfortunately, we can't complain about what we're given, right? But the volume of the others is actually unbounded for the other 2 families. So that there are Berge knots with unbounded volume, so they are certainly not ancestrally finite. Now remember the Berge knots, the slope beta and the slope alpha we're talking about. The one gives you S3, the one gives you the lens. They're at distance 1. I mean, they have to be by the same survey field. Even distance 2, there's a little bit of a problem. It's not so hard to construct examples of manifolds with arbitrarily many cusps, arbitrarily many boundary components, with a pair of fillings at distance 2 that are toroidal. And so, I mean, those cannot all come from a finite set, obviously, because the number of items are large. And so the moral here is that, distance 1 and distance 2 even, you're not going to get this ancestral finiteness. It's going to be slightly more complicated than that. But on the other hand, for distance, for distance 3 and more, maybe it's true. So here's the question, really. I mean, maybe the set of exceptional pairs with a distance big with 3, maybe that's ancestrally finite. Maybe that they all come from just some finite set of pairs, and you can sort of understand them all just by. Yeah. And so that's the hope. And let me just finish by saying, so what's known about this? And well, a distance. See, remember I said that at distance 6 and more, I mean, the set should be finite on the nodes, right? I mean, and that's known modulo this z question. And again, at distance 5, again the answer is known. Again, modulo the case where one or both fillings belong to the small subfield. So modulo that, we do know actually that the set of things is ancestral. In fact, we know exactly what the ancestors are. There's actually 7 of them. I mean, 6 just have 1 boundary component, so they're kind of first generation. There's 1 that has 2, and of course that 1 is the Whitehead sister, right? We saw it earlier that it has 2 fillings at distance 5, and there are infinitely many descendants there, and but that's all you need. That's the whole story. Again, modulo the small cipher problem. When you get to distance 4, again, modulo the small cipher. There's one other problem. And I alluded to this earlier, that we don't know whether there's a toroidal filling and a lens space filling at distance 4. There probably isn't, but somebody needs to prove that. And then once that's done, then again, modulo this small cipher problem. All these guys come from a finite set. We know exactly, again, there are just 7 of them. Now you need 3 that have 2 boundary components. In fact, one's the Whitehead link, so finally then, let me just kind of summarize by listing the problems. I mean, so here's right, so a couple of more slides here. This is the problems on the left. So let's start by the special case of knots in S3, right? So you have one filling that gives you S3, and so the first thing is to prove the K-link conjecture. So that's one. You need to show that you never get a reducible manifold. And I was going to say something that are known about this. It's known that if you do get a reducible manifold, then certainly beta can't be zero. That's the famous property R conjecture was proved by Gabay in 87. It's also known that you have to have a lens space somehow if it's a counterexample. It's also known that it has to be an integral surgery if it's a counterexample. And a very recent result of Josh Green, very nice result, using Hagar for homology, that in fact it can't be a connected sum of two lens spaces. If there was a counterexample, it would have to be a lens space and then plus something that's not a lens space. So, but anyway, somebody needs to finish that up, prove the K-link conjecture. And once you've done that, then now I move to the small cyclic fiber space case. See, the secret surgery theorem says if you get a lens space, then it has to be an integral surgery. The distance from the meridian has to be 1. So the next thing to do, you have to show that that's true for these small cyclic guys as well. And I think the best it's known is about 4 or something. And then once you've done that, then you want to classify the corresponding knots. And as I alluded to, this is a little bit more complicated. It's not quite clear what the answer should be. And finally, for the toroidal guys at distance 1, I mean, we know that, I mean, there are probably too many to really classify. It's certainly not an ancestry finite set. Udavi Munoz and Lukic gave examples where the volume was arbitrarily large. Okay, so that's some of the things you need to do for knots in S3. And then finally, once you've done that, so what's left to do with the more general case, just when you have an arbitrary pair of exceptional fillings on M. Well, you first want to, this special case that I mentioned, that a toroidal filling and a lens space filling, you want to show that in fact that can't be 4. It was shown recently that it can't be more than 4 by Sanyok Lee, but the answer is probably 3. And there are infinitely many sort of well-known examples that come from the 3-chain link that actually realize this. You need to show that those are the only ones. You also need to do the ones where you get a pair of toroidal fillings. Like I said, this is known for distance 4 and more. It's completely classified. So you need to do the same. There should be some finite list at distance 3. One remark here is that at this point you're going to have manifolds with 3 couplings, 3 manifolds. Because the 3-chain link actually has 2 toroidal fillings at distance 3. And so you need to do that. And then finally, this is the sort of hard cases, you have to see what happens when one of your fillings is a small cyclic case. And the problem with that is, I mean, let me just briefly say that, you know, these manifolds, they don't, I mean, if they're infinite pi 1, I mean, they contain Z plus Z, but they don't contain any sort of nice embedded tori. I mean, they don't, you know, there's an immersed torus that you can possibly work with, or there's a genus 2 Hagar surface, which you probably maybe work with. The trouble is, in all the other cases, there's some nice embedded low genus surface that you can actually work with. For these guys, there's really not. But I mean, there's some progress. So one thing you need to do, for example, you want to show that if you had an exceptional pair of fillings on some hypothetical M, and suppose one of the fillings was a cyclic fiber space, and the distance was at least 6, you need to show that in fact the distance, you know, is either 6 or 7, and in fact the manifold is just a figure 8 one. I mean, that would follow from this conjecture that these 4 guys are the only ones. And, I mean, actually, so I finished this because actually Steve Boyer and Jingu Jai and I are sort of working on this at the moment, at least in the case where the other filling is toroidal. We hope that we can actually solve that. But basically, when one of the fillings is a small cyclic, that seems to be the case as hard as to do. But when both fillings are small cyclic, then that's probably the hardest. So this will take us up to 2050.